Just take a look at your phone for a second, or whatever device you're listening on. It's incredible, isn't it? The sheer power packed into something so small.
It really is.
But electronics, well, they weren't always like this. Not even close.
No, definitely not.
So today we're doing a deep dive into a truly pivotal invention, the integrated circuit. And we're drawing heavily from Jack Kilby's own words, specifically his Nobel lecture. It's titled, Turning Potential into Realities, the Invention of the Integrated Circuit.
Yeah, and our goal here really is to get a handle on the massive shift this invention caused. How we went from these enormous power-guzzling machines to this sleek, efficient tech that, basically runs our lives now. It's a story about making things incredibly small, but with just immense consequences.
So before this tiny chip changed everything, what were we using? What powered electronics?
Vacuum tubes, mostly.
Vacuum tubes. Okay, so these were what, large glass components?
Yeah, big components controlling electron flow inside a vacuum. You found them in early radios, military gear, that sort of thing.
And give us a sense of scale. I mean, the ENIAC computer from 1946 is always the classic example, right?
Oh, absolutely. ENIAC is mind-boggling. Over 17,000 vacuum tubes.
17,000?
Yeah, and it weighed 60,000 pounds. Took up something like 16,000 cubic feet of space.
Wow, like a whole building.
Pretty much. And the power consumption, 174 kilowatts. Just think about that. Huge.
So the problem wasn't just that they were gigantic.
No, not at all. I mean, yes, they were too big, too heavy, used way too much power. But a huge issue was reliability.
Okay.
Think about it. Thousands of individual parts. Any one of them could fail. And they did. Often.
So building anything complex was a nightmare.
Exactly. Designing, building, maintaining. It was a massive headache. That unreliability, that sheer scale, it really forced people to look for something completely new.
All right, so the pressure was on, and then came the transistor, Bell Labs, 1948.
Correct. The transistor was a huge step forward. It used semiconductors, silicon, germanium, solid state. Much better than vacuum tubes.
Smaller, more efficient, presumably.
Oh, definitely smaller, more reliable, less power hungry. A big improvement. But...
There's always a but.
Right. There were still discrete components, each transistor, each resistor, each capacitor. It was still its own separate little thing.
Okay, so you still had to make them all individually.
Individually manufactured, and then, wired together, one by one. On a circuit board, imagine building, I don't know, a car engine piece by tiny piece, soldering every connection.
So still incredibly complex to assemble anything sophisticated, lots of connections, lots of potential failure points still.
Precisely. The fundamental assembly problem hadn't really gone away, even with the better components.
And that's the challenge Jack Kilby faced when he arrived at Texas Instruments in 1958. His job was basically miniaturization.
That was the mandate, make things smaller.
And he had this incredible insight. Instead of connecting separate parts, what if you could make all the parts, the transistors, resistors, capacitors, out of the same single piece of material?
The monolithic idea, that was the leap.
And he actually built it, right? Pretty quickly.
Yeah, August 28th, 1958. He demonstrated the first working prototype. It was a simple circuit, a flip-flop, made on a little slab of germanium.
A true solid circuit, everything integrated into one block.
Exactly. And this is key. It wasn't just about making things smaller, although it did that spectacularly well. It fundamentally changed how you design and build electronics.
How so?
Well, you moved from thinking about connecting countless individual bits to designing an entire system on one chip. It wasn't just incremental improvement. It was a totally different way of thinking, a paradigm shift.
And that shift enabled complexity on a scale nobody could have imagined before.
Absolutely. Exponential growth became possible.
And this wasn't just theoretical. It found real-world uses pretty fast, didn't it? Like in the space race and defense.
Oh, yeah. Critical early uses in the 1960s. The Apollo program relied heavily on integrated circuits for guidance computers. The Minuteman missile program, too. These demanded small size, low power, and reliability.
Things vacuum tubes just couldn't deliver.
Not a chance.
And for something maybe a bit more down to earth, didn't Kilby's team also develop the first handheld calculator?
They did, in 1964. A direct result of the IC.
Yeah.
Suddenly you could hold that computing power in your hand.
Amazing. And the impact since then? I mean, the scale and the cost reduction is just astronomical.
It's hard to even grasp.
Yeah.
Those early chips might have had, what, a few dozen components?
Right.
Today we're talking hundreds of millions, even billions on a single chip. And the cost. Kilby mentioned a single transistor initially costing maybe $10.
$10 for one.
Yeah. Now, for that same $10, you can essentially get, well, over 100 million transistors manufactured as part of a modern chip.
That reduction is almost unbelievable. It just changes everything.
It completely reshaped the economy, innovation, everything. It made computing power accessible, almost ubiquitous.
And you see it everywhere now.
Yeah.
Military, space, cars, the internet, healthcare.
It's foundational. Pretty much any advanced technology you can think of relies on integrated circuits.
So looking back, it's quite a journey from that room-sized ENIAC monster
Yeah, all those glowing tubes.
to the invisible intelligence humming away inside the devices we carry every day. All thanks to that initial idea, putting it all on one single piece of material.
It's an incredible legacy. And, that drive for miniaturization, it just hasn't stopped.
No signs of slowing down.
Not really. And every step forward, even if it seems small, has these huge ripple effects. So maybe the thought to leave you with is just consider all that hidden complexity working for you right now and what happens next. What amazing things will these even tinier, even more powerful circuits unlock in the future?